Hello and welcome to the Venn diagrams presentation. Today we're going to be looking at all the ways Venn diagrams can be used in mathematics, touching on a little bit of A-level maths and also looking at some Boolean algebra. It's got a range of material in basically which might at first seem a little bit disconnected, but in fact certainly belongs together, so bear with me on this one. Now, nobody's too certain exactly how they're going to be putting Venn diagrams back into GCSE, and let me assure you that really not that long ago it was part of GCSE. In fact, some of the material we're going through today you'll be surprised to hear was actually taught in Year 7. I was certainly surprised to hear that, but I was shown the Year 7 textbook and shown some very demanding problems, which we'll have a look at the end. So, anyway, without further ado, let's have a little look at Venn diagrams. Now, I've started off with a couple of jokes just to lighten the mood. Here we have a Venn diagram. We have in one circle people who understand Venn diagrams, and in the other circle people who don't understand Venn diagrams. Ha ha ha. Now, I hope you recognise the point I'm trying to get across here, which is that these circles don't overlap, and most people recall that in Venn diagrams the circles certainly do overlap. Well, the one situation where circles will not overlap, or they might put a 0 in the overlap of the circle, is when the two events are mutually exclusive. Now, I'm certain you'll recall that mutual exclusivity in probability just implies that these events can't take place at the same time. They can't happen at once. Somebody cannot both understand and not understand Venn diagrams. It would be a logical impossibility. Okay, moving on to my next little joke in the next slide. We have a Venn diagram of emotions. Here we go. Short-lived happiness, sudden rage, and prolonged suffering. Well, apparently, at the intersection of these three emotions, if you like, is being a sports fan. In other words, if you're a sports fan, you can expect to suffer short-lived happiness, sudden rage, and prolonged suffering. Whereas, if you're only suffering from short-lived happiness and sudden rage, perhaps you're just scrolling through your Facebook newsfeed, and that is certainly an emotion I've felt before when scrolling through my own Facebook newsfeed. You can keep on having a look at that, and you can certainly look at these Venn diagrams with your class if you like, these little funny ones. If you look on the internet, it's amazing how full up it is with comedy Venn diagrams. It seems to be almost an internet meme, a viral meme now. Anyway, let's have a look at another one just to kind of get us our brains in gear into what Venn diagrams really show. Okay, I haven't labelled these sets, and I want you to understand that whenever we draw a Venn diagram, we're actually representing a set of objects. That is something which is very much down right deep in the darkest depths of pure mathematics set theory, but it's something actually which we're going to be looking at in a moment's time. But yeah, can you guess what these three overlapping sets represent? Now, it will help if you know a little bit about languages here, because certainly the answer is certainly going to involve that. I'll just give you a minute or two to pause the video and have a good look at it. Okay, so hopefully you've had a chance to have a look there. Now, the answer is they represent three different alphabets and the letters which those alphabets share. The alphabet which I'm sure you'll recognise is the top right circle, which is clearly our commonly used English alphabet. The top left circle I would hope you would start to recognise as the Greek alphabet, because let's face it, we use so many Greek letters in mathematics that it's it's quite useful actually to know not the whole of the Greek alphabet, but certainly much of it. And once again, I would say that knowing all of the Greek alphabet actually it really does help, certainly in A-level and beyond. But yeah, at GCSE it's not really so necessary, but I'm certain you're aware that those are Greek letters. The bottom set is actually the Russian alphabet, or Cyrillic alphabet you might call it, and as you can see, all three of those alphabets share the letters O, T, H, P, M, A, B, X, K, Y and E, whereas only the English and Russian alphabets share the letter C, the Greek alphabet does not have the letter C, whereas the Greek and Russian alphabets have the symbols, as I'm sure you can see them, the pi symbol, which is capital P. It also has, I believe, the capital G symbol there. That's a gamma symbol, that symbol which looks a little bit like an R. That's just in the Greek and Cyrillic alphabets, and likewise N, Z and I are just in the Greek and English alphabets, but they're not in the Cyrillic alphabet. So there you go. So this idea of overlapping sets is crucial to Venn diagrams, and what I want you to understand is if they overlap in one circle but not in the other, then they are members of those sets. Okay, let's have a little talk about Boolean algebra. Now, George Boole originally came up with Boolean algebra, that's where we get the term from, back in the 19th century, just when set theory was really taking off. It is the algebra of logic, and logic is exactly that which underpins mathematics, and so it's really quite important at a fundamental level of maths. But Venn diagrams are simply a graphical representation of Boolean algebra. Now, the three connectives that we're going to be looking at today are, and they're really the only three connectives you would need in logic. I can pretty much guarantee that really you only need three. They build up more than three. There's things like the excluded middle, XOR, that's used a lot in cryptography and computer science. And if you've done logic gates in computer science, you'll know, NAND, NOR and gates like that, and XOR I believe is in logic gates as well. Well, they can really be built up from these three simple terms of and, or and not. You really just need those three terms to build up everything else in logic. So let's have a look at the symbols for them. And is often called the intersection, and we'll see why in a second on a Venn diagram. I want you to read that it's an N. It looks like an N without the tail at the top. That A intersection B. A and B. Whenever you see that symbol, I want you to read it to yourself as and. Symbol for or, which is sometimes called the union of two sets, it looks like a capital U. And whenever you see that capital U, I want you to read it as or. And then finally the not symbol, or the symbol for negation, is just a little dash next to the letter, so A dash is not A. Those three symbols are what we're going to be using all the way through our Venn diagram practice. Now I'm putting the next bit in just because I'm uncertain whether the new GCSE syllabus will want you to understand the Boolean algebra connection to Venn diagrams. I think it's really useful if you do understand it. So even if it's not going to be coming up in the GCSE, which by the way nobody knows yet because the specification isn't very specific, it merely just mentions using Venn diagrams. I would suspect not actually, but we will see. It's useful to know anyway. But yeah, let's have a look at how all of this ties in to Venn diagrams. Okay, I've got a Venn diagram here, two overlapping sets, set A and set B, and I've coloured some of the regions in. In fact, I've coloured in all of region A and all of region B, including the overlap. Well, that represents the set A or B. That's why underneath I've written A union B. We sometimes pronounce or as union. There's a pretty clear reason why we pronounce it as union. It's because it's the union of two sets. It's where both sets intersect. And I would often encourage students to understand it as or. Yeah? And I always say to students, or isn't strict. Or allows either condition to be true. And I always give the same kind of example. I say, if I said to you that you can walk into this room if you like maths or if you've done your homework, then you could meet either one of those conditions or both the conditions and you would be allowed into the room. In other words, people who like maths would be allowed into the room, people who've done their homework would be allowed into the room, and people who like maths and have done their homework would also be allowed into the room. Now this takes us nicely onto the next Venn diagram, and I want you to bear in mind the set on the left is still set A and the set on the right is still set B. I've only coloured in the intersection here, and as you'll recall, the intersection means and this represents A and B, and that's why underneath this Venn diagram I've written A and B. Now, if I say you can only come into the room if you've done your homework and you like mathematics, then you would have to meet both those conditions to come into the room. And that's why we only shade in the central region here, because you have to satisfy both the conditions. And is strict. It's only true if both the conditions hold. And therefore with and or the intersection, we shade in the middle of the Venn diagram. Now if we look at the next Venn diagram, we see a Venn diagram of not A. Now why is it not A? Well, because quite simply, I have shaded every single thing in which isn't A, and therefore it's not A. Now, these kind of Venn diagram regions, you're going to have a chance to practice these very soon, because I'm going to give you a little, there's a little practice sheet in the module. It's really quite tricky to get your head around this Boolean algebra. You will make mistakes at first, but that's absolutely fine. It's normal, just have a practice at it. We're going to have a look at a few more as well. Let's have a look at the next Venn diagram. Now, if you look underneath, this represents B and not A. Why does it represent B and not A? Well, because I've coloured in all parts of the Venn diagram which are part of B and, crucially, not part of A. And that's why the intersection hasn't been coloured in here. That's why we've got that kind of half moon colouring in, because we're just shading in the parts which are part of B and also not part of A. If we look at our next Venn diagram, we've got kind of the opposite. Now, this is actually, the simplest way of writing it is B or not A. Now, students find this bit really hard to get because they presume that OR is strict, like AND. OR isn't strict. It's allowed to be anything which is B, or it's allowed to be anything which isn't A. But OR is casual. It's not strict. You can colour in anything which is B or anything which isn't A. And that's why all of B is coloured in, or everything which isn't A is coloured in. Now, lots of students will say to me, but why have you coloured in the middle? And it's quite simple. It's because it's allowed to be B or not A. It's allowed to be either. OR is relaxed, it's casual. You can meet either condition. And that's why we colour in the region there. Now, for the students who find this really quite tough, I often point out, this isn't a perfect rule, but it's a reasonable rule of thumb. OR is always 3 regions coloured in on the Venn diagram, and is always 1 region coloured in on the Venn diagram. You'll notice that in the previous Venn diagram there was just 1 region coloured in, whereas on this Venn diagram we've got 1, 2, 3 regions coloured in. That's always the case for OR and unless there is a bracket involved, and this brings me to the last Venn diagram that we're looking at. Now on this one, everything's been coloured in except the intersection. What would this be? Well, it's really quite tough to get students to see this. There's 2 different ways of going about it. But hopefully they will see straight away that it's 3 regions. So it must be something to do with OR. Well, the fact is, we've coloured in everything which isn't A or everything which isn't B. And that's why this one is actually not A or not B. If you allow for brackets, my AND is 1 region or is 3 regions suddenly doesn't work. If you allow for brackets, you can actually take the complement of what you'd coloured in before. So if you look back at the second Venn diagram when we had A and B, if we wanted to take the photo negative of that and colour in everything which isn't coloured in and uncolour in everything which is coloured in, then we just need to apply a not to that whole expression. And that's why the not of A and B is not A or not B. Now what you've just met there, the fact that not A or not B equals, in brackets, A and B, the negation of that, what you've just learnt there is the first of De Morgan's laws. Now, we're going well beyond the course here, but, you know, why not? De Morgan's laws are really quite useful. I always show them to the students straight away because I hope that, certainly the bright ones, they seem to see it quite quickly, actually, and they recognise, oh, okay, this is basically a rule. By the way, it works completely the opposite way round. If I have not A and not B, which is actually just the outside area of the 2 circles, that equals, in brackets, A or B with a not outside. In other words, if you apply the not through the brackets, then you're going to turn the symbol upside down. And there we go. That is Venn diagrams with 2 regions. Now I know what you're probably thinking. You're probably thinking now, I thought I understood Venn diagrams. Now I realise they're really quite tough. Well, yeah, that's the truth of it. Venn diagrams are actually very difficult things to get your head round. You can represent things quite simply on a Venn diagram, and they're certainly shown, I believe, at primary school. Schools will often show students Venn diagrams, and good thing too. But if you're dealing with it in a logical context with Boolean algebra, it can rapidly confuse. Well, the good news is we've got Venn diagrams with 3 overlapping regions to look at now. Now, I've just put this on its own at first. Perhaps, you want to take a few minutes to try and recognise what the Boolean algebra statements would be that accompany these 6 diagrams here. Try and come up with something. Well, I've called them P, Q and R this time round. Maybe you can recognise the first one, second one or third one. Come up with a series of Boolean algebraic statements which you would associate with each one of those Venn diagrams. Pause the video for a second. We're going to go through an answers in a moment. Okay, so the answers. Well, as you can see in diagram A, we've got P and Q overlapping, and R could just disappear here. This is nothing to do with R. This is just the overlap of P and Q. And so this is just P intersection Q, or P and Q. The next one is a bit more difficult because we will need to use 3 letters here. This is the intersection of Q and R, but it mustn't be in P. How are we going to write down that? Well, we want the intersection of Q and R, so I'll write Q intersection R, or Q and R, but we also want it not to be P. So that's Q and R and not P. I don't need to use brackets there, but some students choose to, and that doesn't make it incorrect. So that's absolutely fine if you have used brackets round some of those expressions. Okay, right, let's move on to the next one, which is quite simply Q or R. That's because P has nothing to do with it once again. So this is the union of the 2 sets Q and R. That gives us Q union R, or as I prefer to call it, Q or R. Diagram D is everything which is in Q but not in P or R. Now there's 2 ways of writing this down. I would put it as Q and not P and not R, but I would like to quickly use De Morgan's laws and point out that's exactly the same as writing Q and P or R not. Yeah, because De Morgan's laws say that not P and not R is the same as P or R not. And that's the answer to diagram D. Diagram E is a bit nicer. It's where we've got P and Q and R. It's the intersection of all 3 circles, so we just write P and Q and R. And finally, in diagram F, well, we want everything which is in P and Q, but also not in R. So we'll take the union of P and Q, and then not R. Quite simple really, and so we end up with P or Q and not R. And I've put the brackets in there really to help you visualise what's going on, but they're not actually strictly necessary. I hope that wasn't too demanding. You're going to have a little worksheet on doing that anyway yourselves. Like I say, I would like to put in a word of caution that I'm not certain that this will necessarily even be included in the GCSE. It's certainly part of the first module of A level though, and it doesn't hurt to learn these things and understand them. And like I say, also, I guarantee this used to be taught in year 7 as soon as students arrive when they're 11 years old. Exactly this Boolean algebra set notation with Venn diagrams. I've seen the textbook and I was really quite surprised when I saw it. Right, why am I showing you all this? What has this got to do with statistics? Well, Venn diagrams are particularly useful for establishing the probability of events that may occur at the same time. In other words, events which aren't mutually exclusive, like the joke Venn diagram I showed you at the start of the presentation. Now, in GCSE, it's likely that they'll probably just use 2 events, I would suspect. So there won't be 3 circles overlapping. There could be, I don't know. But I'm going to deal with a situation where we've just got 2 circles overlapping. Like I say, this is all really unknowns when it comes to Venn diagrams and what the questions are going to look like in GCSE, because the specification is not that specific, and I'm sure you've noticed that yourself when you've looked at it. Anyway, here's a good example of a fairly simple question which you might get, which looks at Venn diagrams and probability. Okay, in a sixth form, 20 students study physics and 42 students study maths. This is A-level physics and A-level maths. You're going to have some students studying both. Well, 10 students study physics and maths. Now there's 100 students in the sixth form. Find the probability that a randomly selected student studies A, physics and maths, B, physics, C, maths but not physics, and D, neither physics nor maths. Now the wording is very difficult in these kind of questions, or it can confuse students anyway. Pause the video if you like and try and have a go with it on your own. Try and set up a Venn diagram displaying this information. Right, when constructing Venn diagrams for these kinds of problems, I always advise my students, if they can, do everything they can to find the intersection first, the overlap, the middle of the Venn diagram. Now the good news in this particular question was that we were told that 10 students study maths and physics, and so I can put 10 in there first. The reason why I want to do that is because my circle for maths must contain in total 42 students. Therefore I know 32 goes outside. That 32 represents all the maths students which aren't studying physics as well. Likewise, on the right hand side, we know 20 students studied physics overall, 10 study physics and maths, so 10 of them study physics but not maths. This would be P and not M in Boolean Algebra. Now, students often don't draw the rectangle, and it makes me quite cross when students don't draw the rectangle around a Venn diagram. Maybe cross is going a bit extreme, but it always irritates me a bit. And that's because it is a closed set. Now you might notice that I used in my joke Venn diagrams, 2 Venn diagrams or 3 Venn diagrams at the start of this presentation where a rectangle wasn't drawn around it. You're absolutely right to notice that, and I would always draw the rectangle around it because it is a closed set and it really should be drawn. Now the reason why I'm emphasizing this is because we have a number outside the Venn diagrams, and we should do quite often. That number is 48, and it represents all the students in the school who do not study maths or physics. Lots of people don't, that's completely understandable. Now, once you've drawn a Venn diagram, it's relatively easy to work out the probabilities. Our first question was, find the probability that a student studies physics and maths. Well, that would be 10 out of 100, or 0.1. Our second question was find the probability that a student studies physics. Well, that's pretty easy as well, because that's just going to be 20 out of 100. We didn't really need the Venn diagram for that. That's 0.2. But by part C, you definitely do need the Venn diagram, I would argue. Maths but not physics. Okay, that is the 32 students to the left of that Venn diagram. As there's 100 students involved in total, we've got 32 divided by 100, and that answer is 0.32. Finally, our last question was find the probability that a student studies neither physics nor maths. Well, those are the 48 students outside the circle. That would be probability of in Boolean Algebra, it would be it would be not M and not P. And yeah, it would be 0.48, or 48 divided by 100. I hope that makes sense. Now, just before we move on, I wanted to show you this question, which I did obtain from a Year 7 textbook, because I think it gives a good example of how Venn diagrams can be quite tricky indeed. Now, it doesn't mention probability, but it would be relatively easy to turn it into a probability statement. A pencil case contains 20 pens that are red or blue. Of these, 8 are blue and 6 don't work. How many of the blue pens do not work if there are 8 red pens that do work? This is a typical kind of tricky question, isn't it? Have a go at drawing a Venn diagram and see if you can solve it. Pause the video, please. The first number we can fill in this Venn diagram is, well, it's quite tricky to see. We know that there's 8 blue pens in total, and we also know from the information that they gave us that there's 6 pens which don't work. Now naturally, we can immediately discover actually that there's 12 red pens, and also that there's 14 pens which don't work. Now just drawing this Venn diagram is confusing for a lot of students, because what they'll often do is blue pen in one circle, red pen in the other. But those events are mutually exclusive, and Venn diagrams aren't really that useful for showing mutually exclusive events, apart from my joke Venn diagram which I showed at the start, but we don't really use them for showing events without overlap, and that's why Venn diagrams normally overlap. And that's why in this example you want blue pens and pens that work. We've now got 4 regions on our diagram, and each one of those 4 regions represents blue pens working, well, that's the intersection. Blue pens not working, that's the region on the left. Red pens that work, that's the region in the circle on the right. And finally, outside the 2 circles is red pens that don't work. I hope that makes sense. Well, what can we fill in first? Well, we're told 8 are blue, 12 are red, 6 don't work, therefore 14 do work. Now, we also know that 8 red pens do work. So straight away I can fill in the region on the right as 8 because that represents red pens that do work. Now, as I know there's 14 pens in total that do work, I can now fill in the intersection as 6. I also know that there were 8 blue pens in total, so outside that region must be 2. And I also know that there were 20 pens in total, and therefore outside that region must be 4. And so the answer is, for how many blue pens don't work, there are 2 blue pens that don't work. There we go, a nice tricky question for you. This has been quite a long presentation in the end, so I'll cut it short here. I hope you enjoyed it, and I hope it hasn't confused you too much, but what I would say, I would like to finish on, Venn diagrams are not straightforward. Make sure you do fully understand it and have a really good go at any of the questions in this module. Okay, thank you very much, and yeah, I hope you enjoy the next presentation, which is on probability and logical fallacies. Bye bye.